opportunity to be part of this workshop. Thank you. Let me share my slides.
Yes, please, sir.
These slides are visible.
Yes, sir. Can you make it full screen now?
Full screen. Here that I will. Now is it visible?
Yeah. Yes, sir.
Okay, thank you very much, and good morning everyone. So actually today's talk is on signal processing and machine learning based frameworks for medical applications. So in this talk we will see use of signal analysis techniques and machine learning approaches for the development of automated systems which can classify different kind of actually brain signals. And signal analysis actually plays an important role here. It gives you nice set of features, and they can be used as diagnostic set of features, or they also actually they can be interpreted in terms of the level of the disease. So this is actually one of the major role of signal analysis techniques in interpretable AI or explainable AI. And here we will see how these actually even feature itself, like analysis level and itself, they are able to identify the disease. And after that, these features, whatever actually we have proposed, that will be used for developing automated systems for classification process using these machine learning concepts. And also there have been two directions in the literature for this brain signal processing, especially the electroencephalogram EEG signal processing. So in one case, actually we consider channel-wise EEG signals. So for individual channel, we take a separate EEG signal and we process it. And other case, we go for multi-channel scenario. So like we take all signals into consideration, like all EEG signals together, and we do joint analysis. And actually after that, that can be used for analysis and classification. So these both frameworks, univariate EEG signal processing and multivariate EEG signal processing, together with this classification approaches, machine learning concepts, will be actually explored for various applications in EEG signal processing, like as epileptic seizure detection, sleep stages classification, emotion detections, that actually will be explained. So with this background, let us start this talk. So this is the actually overview of this talk. First we will see introduction, then we will see the motivation for this electroencephalogram EEG, what is the need of EEG, what is the signal about that we will see. And after that, there will be two parts of this talk. One is univariate analysis of EEG, and second one is multivariate analysis of EEG. Univariate analysis of EEG, we take actually individual channel for the processing, and multivariate analysis of EEG, we consider all channels together. So in univariate analysis of EEG, we will see analysis and classification and detection of the epilepsy using EEG signals, but that will be based on the univariate concept. And after that, we will see time frequency image based features for classification of sleep stages. And then actually we will see multi-wavelength decomposition based features for human emotion classification. So these actually, after that, we will see multivariate scenario, and where this multivariate empirical mode empirical is wavelet transform, that actually that we have proposed, and we have shown that it it is better than the empirical mode decomposition that was proposed for multivariate case. And also this is the extension of the univariate empirical wavelet transform that has been proposed in the literature. And then actually its applications for epileptic seizure detection will be explained, and in the end conclusion will be provided. So human brain actually is very complicated, and it is highly nonlinear system. It is actually like even you record EEG signals from the human brain, at a time 4 or 5 trials, and they all will be different. So actually, is a lot of variability is there. And this electroencephalogram, which we call EEG, is measures the electrical activity which is generated by the neurons in the brain. So, like in human brain, there are actually multi million neurons, million neurons actually, and they connect each other to generate the electrical activity, and which is measured by the EEG signal. And this EEG signal is actually very useful clinical tool, and even like it is a kind of signature which we use to detect the disease, and even go to hospital if anyone has brain related disorder, brain related problems. If you go to hospital, then they will take your EEG signal. So this is really one kind of initial signature, initial tool which detects the abnormality, and this is commonly used for the investigating different physiological and pathological states of the human brain. And this actually analysis, we want to extract the information from this signal, EEG signal. So then that there are two ways. One is like that generally in hospitals doctors do, they perform visual scanning of the EEG signal. And second way is like these days this is the age of computers, and everybody is using computers, and we want to have computer aided medical diagnosis, and we want to use computer for performing the analysis of the EEG signal. So that is the whole purpose of this talk. We will see how these frameworks which are based on the signal processing and machine learning techniques can be used to develop the automated system or computer aided medical diagnosis system. You just give the EEG signal, it will tell you what is the disease, what is the level of the disease. And this quantitative analysis of EEG signal is a very challenging task because the signal is very complex, it's complicated, and it's irregular nature. So like if you see the EEG signal, it does not have any, like it does not look like have any symmetric kind of nature or any well defined nature. So it looks like a chaotic noise kind of signal. And this is also actually studies have shown that the signals actually EEG signals are the non-stressing nature. So non-stressing nature means like in signal processing we use mathematical models to represent the signal. If any of the parameter of this model is changing with time, then we call them non-stressing signals. So this EEG signal actually falls in this category, where if whatever model you use, even if you go to very low scale, a very low interval of time, a very low duration or less duration, then also actually you find these EEG signals model that we use, they actually vary with time. So this is highly non-stressing signal. And what generally these doctors actually do in the hospitals, they perform visual scanning of EEG signals. So like we uh, uh, record EEG signals by the electrodes cap from the subject, and we print these EEG signal waveforms on the paper. And that paper generally doctors actually they visually scan it, and then that basis they perform the diagnosis of the brain diseases. And such kind of methods where we perform visual scanning of EEG signals is very time consuming, because you have to take printout, and sometimes actually the seizures are repeating, maybe in the daytime you have 2 3 seizures, and then actually every time you are taking recording signals, taking printouts, so it is like very time consuming, and it may be inaccurate also. So like you are taken printout of half an hour EEG signal, so sometimes the variations will not be clear. And if you are taking printouts for a small low interval or less interval, then actually you need to take huge printouts. So due to that, actually it is very time consuming, it may be inaccurate also, and it is very complicated when you use this EEG signal for long term monitoring, like a patient is admitted in the ICU and we have to always monitor the EEG signal. So such kind of methods actually have a lot of limitations, and it's very complicated, and it is subject to judgment and suffers from human errors. So like if you ask somebody, like the person sometimes you might have seen in the hospitals, like patients, they have family members, they say, let us have opinion of other doctor. So like whatever decisions making done by the one doctor, generally people are not agree with that. So they go for other doctors or like that. So such kind of methods for the diagnosis, they suffer from human error. And also this kind of scanning that we do in hospitals, that is generally performed by the trained professionals. So due to these reasons, there is actually a lot of interest in the literature to use signal processing and machine learning algorithm to design these automated systems, which you also call intelligent systems, expert systems, and computer-aided medical diagnostic systems. So where nicely you can perform automated analysis and classification of EEG signals, which will tell you whether this person is suffering from that disease or not. So the normal case, abnormal cases, different stages of the diseases actually can be classified using such kind of systems. So the first part of this talk will focus on univariate analysis of EEG. So for that actually we have proposed these frameworks that we will discuss one by one. So in first framework, we have actually empirical mode decomposition based features have been proposed for analysis of normal and seizure EEG signals. And we have also proposed classification of seizure and non-seizure EEG signals and detection of epileptic seizure. Non-seizure means it includes like a normal as well as seizure free. So like seizure free means earlier they were the patient of epilepsy, but now treatment has been done and now they are seizure free. So normal and seizure free, when you combine, normal means they never had epilepsy disease, and such combination gives you non-seizure. And after that actually this time frequency image based features also we have proposed for classification of sleep stages that we will see. And that actually we have studied on two well-known standards. One is RNK standard, second one is American Academy of Sleep Medicine standard that is recently proposed. And after that we will see this multi-wavelength decomposition based features for human emotion classification. That is actually, so this is all these approaches they are based on the univariate EEG signal analysis. Actually there are three main steps in the computer based analysis of EEG signals: for analysis, then classification and detection of epilepsy. So for each part we have actually proposed a framework based on the empirical mode decomposition. So this epileptic seizure, this is also known as epilepsy. All seizures are not epileptic seizures, but when your seizures are repeating, they have some frequency, then they call epileptic seizures. So they are the outcome of the transient and unexpected electrical disturbance of the brain. So like in brain, there are a large amount of neurons, and they sometimes they synchronize together and they generate very high electrical activity. So due to that actually this electrical current has very high value. So this due to that actually brain becomes unbalanced, and the brain is the actually master of the body. When brain is disturbed actually then everything is disturbed in the body. So it is serious disease, and it affects around 2% population of the world. And we have proposed area parameter for analysis of normal and epileptic seizure EEG signals, the bandwidth parameters for classification of seizure and non-seizure EEG signals, and the instantaneous area for the automated detection of epileptic seizure. So these three frameworks based on the EMD that will be actually EMD means empirical mode decomposition will be explained in the coming slides. Let us have brief background for this, what is the need of EMD method before going ahead. EMD actually is the recent, not recent, like 1998 it was proposed by Wang and others, and this is data adaptive signal processing technique. So it is different than the conventional methods actually we use in signal processing. So like in Fourier transform, that was actually simplest technique, analysis technique. It was proposed by the Fourier in 1807. And in that actually in Fourier transform, we represent signal in terms of sinusoidal functions. And these sinusoidal functions, they are periodic functions. They exist from minus infinite to plus infinite. they have actually infinite spread or duration. So due to that, actually resolution, localization, concentration, that is proportional to 1 upon spread. So these sinusoidal functions, due to infinite duration, they have actually zero time localization or zero time resolution, and due to that they are not able to represent non-static signals. Actually, that is most common in real life. So like the EEG signal is also one such kind of signal where these parameters of the model changes with time. But when you have sinusoidal functions in the representation, that is the case of the Fourier transform, their parameters are not changing with time, amplitude, frequency, phase, they are constant. So such kind of basis functions, they are not actually suitable for representing these non-static signals, kind of like a EEG signal. So in order to have analysis of such kind of non-static signal like EEG using Fourier transform, the short time Fourier transform, STFT, which was proposed in the literature. So in STFT, short time Fourier transform, what we do, we divide this signal into different print segments, and each segment we assume that signal is stationary, and then actually we apply Fourier transform, and then arrangement of these Fourier transform different segments gives you the actually short time Fourier transform, STFT. And STFT, there is no thumb rule which will
Sir,
suggest us like what should be the, yes.
excuse me, sir. Sir, the presentation is not visible.
So slides are not visible. Could you please
Can
see
can you
are you able to see
can
the
you?
block diagram?
Yes.
No, sir.
Oh,
Sir, can you
then
reshare it once again?
which slide is coming?
No, sir. No. No, none of slide is showing right.
Oh, but it is showing presenting all these things.
Sir, can you
Okay.
reshare it once again? Yeah.
Yeah. Hmm. Actually, it says that only meeting organizers can share. Dr. Rahul ji?
Yes, sir. 7 minutes. 7 minutes.
Yeah, yeah. This may be the reason.
But I'm not changing any settings, sir. Uh, 1 minute.
Okay. Could you please share these slides from your side, then I can present from here?
Yeah, yeah, sure, sir. Sure, sir. Please
Okay.
send it.
Okay.
Please send us a reply to my last mail, sir. Yes.
Yeah, yeah, I'm just.
It's happening.
I have sent.
Yeah. Yes. I will. Until
Have you received my email?
not yet, sir.
I have sent.
Okay, we'll check. Yeah, got it, sir. Right.
Oh.
Hello, is my screen visible, sir? No?
Yes, yes.
Yeah. Okay,
Just
fine.
yeah. This was this.
Yeah.
So could you please go to that block diagram? That was next slide. Oh. Hmm. Okay, previous. Yeah, good. Thank you. Thank you. This one only. So this actually now slides are visible.
Yes, sir.
Yes, sir,
Okay, okay.
visible
Thank you.
but not in presentation mode, sir.
Hello.
Sir, visible but not in presentation mode.
So actually, I have sent one PDF file also. PDF file, could you please open? I think then it will open in the complete screen. Yeah, this one PDF. This problem will not come there. Control L. Yeah, now it is fine.
Yes, sir, fine.
Yeah, very good. Now go to the blog. Yeah, yeah. Thank you. Yeah. So in the actually in HTFT short time Fourier transform, we use actually windows, and there is no thumb rule which will suggest what should be the size of the window, type of the window. This is based on the trial and error. And sometimes when your signal has low frequency component, then you want to have wide analysis window, and the high frequency component need narrow analysis window. That flexibility is not there in the HTFT method, short time Fourier transform. Then actually this wavelet transform concept was proposed. So in wavelet we use scale concept, mother wavelet, and by using scale we generate different kind of daughter wavelets. So when you see the mother wavelet at low scale, it gives you the basis function which are suitable for high frequency component. And when you see this wavelet at low scale, large scale, then it gives you the basis functions that is suitable for low frequency component. So high frequency component you are analyzing using low scale, so it's good time resolution. And on the other hand, you are analyzing low frequency component with the large scale, so which gives you the poor time resolution. So in that way, multi-resolution analysis can be carried out using wavelet transform concept. And one good thing in wavelet transform is that actually it can be implemented using filter bank concept. So like you take signal and apply to filters, low pass, high pass, and downsample by 2 each part, and you will have nice approximate detail, and further you can decompose them. So in that way, this wavelet transform can be implemented, that we call discrete wavelet transform, DWT. There also actually some issues are there. For example, there is no rule which will tell us how to select the mother wavelet, like which kind of signals that particular mother wavelet is suitable, that we don't know. And also how many level of decompositions are required to represent a signal. So that actually these are the problems. So motivated by those problems, in 1998 this Ohang and others, they come up with this empirical mode decomposition, and it is actually fundamentally completely different than Fourier transform, wavelet transform, short time Fourier transform. In STF, short time Fourier transform, wavelet transform, and Fourier transform, we design basis functions from our side. So like basis functions are man-made, and these real life signals, they are natural, and we represent these natural signals, real signals, in terms of the functions which we have designed. So this is like forceful representation actually. Signal is not sinusoidal, signal is not wavelet, signal is not windowed sinusoid, but forcefully we are representing them in such kind of basis functions. Here, empirical mode decomposition situation is different. So here, we actually whatever real life signals you have, and you can extract basis function from the signal itself. So that is like adaptive method. So we call them intrinsic mode functions, because basis functions, whatever you obtain from the signal, that is actually intrinsic mode. They are part of the signal. So these basis functions we extract from the signal, and they are data dependent adaptive method. So it doesn't require design of the basis functions. So in actually some way it is expected that because this IMFs, since they are part of the signals, they can be more physiologically important for brain signal analysis, because they can give you more insights because they are part of the signal itself. So motivated by that, these actually features of the EMD method, we have actually explored this EMD method for this EEG signal processing. And so in this block diagram, you can see there are three methods. So three frameworks. One is for analysis, second one is classification, and third one is for detection. So we take EEG signals, then we apply EMD method. It will decompose this EEG signal into set of IMFs, and that IMFs means intrinsic mode functions. And then actually we use Hilbert transform to obtain these analytic signal representations of these IMFs. So in first case, we actually area feature based on the modified center tendency measure is computed. Then we have checked using this Kruskal-Weiss statistical test whether this area parameter is significant or not in order to describe normal and seizure EEG signals. And then second methodology, we have computed amplitude modulation and frequency modulation bandwidth features. And then these features are given as input to least square support vector machine classifier. Then nicely you can say classify seizure and non-seizure EEG signals using such kind of features together with machine learning classifier, which is implemented using least square support vector machine. And third methodology, we have actually instantaneous area features have been computed from this IMFs, analytic IMFs, and then they are giving actually as input for decision rules. So there is some decision rules actually we have defined, so which ensures that whatever decisions you are making for this epileptic seizure detects that is reliable in nature. And then actually we have epileptic seizure detection based on these rules. So these all three frameworks will be explained in the coming slides. Next slide, please. So for this study, this EEG data set, which is actually publicly available with the University of Bonn, Germany, has been considered here. And this data set includes 5 subsets: Z, O, NF, and S. This Z, O, these are the actually, Z is eyes open EEG signals subset. O represents the subset which is formed by the EEG signals collected during eyes closed condition. And subsets N and F, they represent actually EEG signals under seizure-free case, and subset S represents EEG signals from the seizure class. So in that case, way, this entire data set actually has majorly 3 set of EEG signals: normal, seizure-free, and seizure. And each subset has 100 EEG signals, and in that way total 500 EEG signals are there. And each signal's duration is 23.6 seconds. And the sampling rate for the EEG signals in this data set is 173.61 Hertz. And these signals have been recorded using 128 channel amplified system based on the common reference. Next slide, please. So already that we have seen this EMD method actually has been used here for the analysis purpose. So which is suitable for nonlinear non-seizure signals, and is adaptive method, does not require any condition of the stationarity. Whatever signal you give, it will decompose it into set of IMFs, and does not require design of basis function like sinusoidal function, Fourier transform, wavelet and wavelet transform. And the EMD method actually can decompose signal into set of narrowband intrinsic mode functions IMFs. And these IMFs can be modeled using AM and FM signal model. Like in sinusoidal functions in Fourier, we use amplitude, phase, and frequency are constant with respect to time. But here we allow them. So once your amplitude is varying with time and frequency is varying time, that gives you the amplitude and frequency modulated signal model. So these IMFs actually are considered as a AM/FM signal model. Next slide, please. So actually, this is a simple EMD is a kind of algorithm. Instead of this, like generally when you see signal analysis like Fourier transform, wavelet transform, you find the mathematical equations. But here it has from actually computer science researchers. So they have given as an algorithm in the form of algorithm, and by using this algorithm, like a recursive algorithm, one by like you have different iterations to obtain the residual, and from the residual we satisfy IMF conditions. Once these conditions are satisfied by the residual, which is obtained by based on the maximum minima of the two inbuilt maximum minima of the signal, and from that we generate two envelopes, and then based on the average of these two envelopes, we subtract that actually that component from the signal that we call residual. So that residual should satisfy these two conditions. They are very important conditions. So the number of extrema and number of zero crossings must be the same or differ at most by 1. So this condition ensure that like whatever IMFs we obtain, they are like sine cosine function, and the mean value of the envelopes, which is defined by the local maxima, local minima, is 0. So this condition ensure that whatever IMFs actually you obtain, they are symmetric in nature. So after this iterative algorithms, recursive relations, in the end we can represent this actually signal in terms of IMFs and the last residual, from which further IMFs cannot be derived. So the equation 1 you can see that is the final outcome of this method, where you have set of IMFs plus residual. Next slide, please. So here you can see one example of this empirical mode decomposition of EEG signal. So like a signal actually that has epileptic seizures and nature, and it has spikes and large amplitude. So these are the two inherent features when we doctors they detect this as a seizure. So it's the spikes and it's a large amplitude. So you can see in this epileptic EEG signal, and this is decomposed using EMD method. So first IMF gives you the highest frequency present in the signal, and the last 8th IMF gives you the lowest frequency present in the signal. So the first IMF, that is actually this is the corresponding to the lowest scale of the data. So this is like details, and similarly 8th IMF represent the largest scale of the data. This is like approximation. So in that way, you have signal can be represented in terms of approximation detail using EMD method and without designing any wavelet, any basis function. This is actually beauty of this method. And adaptive, you just give any signal, it will decompose into number of components. Next slide, please. So here, actually these IMFs can be represented by AM/FM signal, and in this method, whatever we have proposed, this is based on the analytic signal representation of the IMFs. So each IMF is converted into analytic or complex IMFs using Hilbert transform, that you can see equation 2. And this analytic signal representation actually satisfy two very important conditions, useful conditions. The plot has directional rotation, and the rotation in the plot has unix sense. So this is very useful for actually our feature that you can see in the next slide, please. So here you can see when you see the analytic signal representation of the EEG signal without any decomposition, there is a presence of multiple centers. There is no specific geometry. On the other hand, if you see the analytic signal representation of IMF 1, 2, 3, 4, then you have nice circular symmetry there, and they can be used to detect the area parameter. So we have defined area parameter due to this nice circular symmetry that is actually available in this representation, and there is unix center. And if you see Hilbert analytic signal representative EEG signal, there is no unix center. On here, unix center, and the direction of rotation is also clear. So that actually helped us to, or motivated us to define the area parameter to define this, to measure the epilepsy disease attack. Next slide, please. Now, how to compute this area parameter in automated manner? So for that, actually, we have proposed this modified center tendency measure that is given by equation 3. So it tells us what are the for a given radius, how many number of points are lying in that radius. So based on that, actually we have used 95% CTM. So like in the radius which covers 95% of the total points, and that is actually to compute the area. So area is computed by using the simple equation that we have studied in our school time, that A equals to pi r square. And next slide, please. And here actually you can see this, once you compute this area, then we have actually extended this for the instantaneous area concept. So we have actually IMS, we divide into different windows, and then each window we compute the area and then we interpolate it, then it gives instantaneous area, and that instantaneous area of mth IMS is defined by equation 4, and which can be actually used to detect the seizures at any point of time. So the size of the window in this study has been considered, that is 3,840 samples. So that is based on the literature, and based on that actually we have proposed the instantaneous area concept. Next slide, please. And other methodology that amplitude modulation and frequency modulation bandwidths actually of the analytic IMFs have been defined. This is actually is very interesting concept. Like whenever we talk about the bandwidths in the literature, we always say the spread of the frequency in the frequency domain, or spread of the spectrum. And here actually this bandwidth is defined from non-stationary signal representation point of view. So like a bandwidth depends on the two parameters. One is amplitude modulation, second one is frequency modulation. So the bandwidth component corresponding to amplitude modulation is known as amplitude modulation bandwidth, and the bandwidth component corresponding to frequency modulation is known as frequency modulation bandwidth. So these two bandwidths can be defined actually for AM/FM component only, and real life signals are not AM/FM, they are multi-component AM/FM. They are like a wideband signals. So how to get a mono component or AM/FM signal? So that actually this is the EMD method helps us to get the mono component signal, which can be represented by AM/FM signal, single tone AM/FM signal, monocomponent AM/FM signal, and that help us to define these bandwidths. So EMD actually decomposes the signal into such components where these bandwidth parameters can be computed. So bandwidth due to AM and bandwidth due to FM, that have been considered as a set of features for defining the feature space, and then we have used this for the classification of seizure and non-seizure EEG signals. Next slide, please. So now we will see some results for all these three frameworks. First part is analysis of normal and seizure EEG signals. So that SAM, actually this Bonn University database has been used, where subset Z from the normal class and subset S from the seizure class. And EMD based method help us to decompose this signal, actually EEG signal, into components IMFs, where 95% of the data can be covered in the analytic signal representation. And this area parameter has been studied for various cases, window cases, like 500 samples, 1000 samples, 2000 samples, and 4000 samples. Next slide, please. And here you can see this plot of the CTM in terms of percentage of reversal radius. And if you see that in case of normal, the requirement of radius is very less in order to have 100% CTM. On the other hand, for the seizure case, requirement of radius is actually large in order to have 100% CTM. So it shows that in case of seizure, there is a large variability. So area parameter is larger. On the other hand, in case of normal data, normal EEG signal, this variability is less. So the area parameter is also less. So that actually motivates us to use this parameter to identify the seizure and normal classes of the EEG signal. Next. So these are some results for different window lengths, like 4000 samples. You can see the first 4 IMFs, they are able to show the difference between seizure and normal classes of EEG signals. And here probability value is coming out to be 0. So this probability value, this Kruskal-Weiss statistical test, is coming less than 0.05. Then we call it statistically significant difference. And the same thing actually is true for different analysis window. And biomedical signal processing, we always want that our analysis window, the data actually should be less in order to have the decision. So because it is suitable for real-time implementation, also from the patient point of view, he will be in more comfort zone because he has to provide less amount of data. So due to that reasons, we always want to have the method which we are proposing, it should work on less amount of data. So this is also one of the motivation to study the length of the window size or size of the window, which is actually sufficient for this statistical analysis. So next slide you can see here we have studied. Next slide please. 2048 samples. Next slide please. Here 2000 samples. Next slide please. 1000 samples. Next slide please. And 500 samples. So you can see even 500 samples also, if you take the size of the window, analysis window, then also these two classes are statistically significant different. So you can classify like seizure and normal classes in a statistically significant manner. Next slide please. And that actually whatever you see in the form of this graphical, that you see in the form of these numbers. So like quantitative, like the whatever that was the visual representation, here you have same number. So in this table it can be seen for normal and seizure classes of the EEG signals, different window size, the area parameter larger for the seizure case and it is lower for the normal case. Next slide please. And there has been actually a lot of interest in the literature to classify these classes using machine learning, this computational intelligence techniques. And people have used various researchers have proposed various signal processing machine learning techniques, and you can see right hand side, right, the last column, various classification accuracies have been achieved. And our proposed method, this is actually based on the area parameter, and this is a simple analysis. So that actually there is no need of the machine learning algorithm which gives you the 100% classification just based on the simple threshold. So selection of the spoon depends on the type of food. If you want to have noodles, then use fork because your food is similar to the spoon that we are using to have the food. So similarly, luckily, we have got good analysis technique, empirical mode decomposition, which is actually highly suitable for the EEG signal. So that analysis part itself is actually sufficient to provide you better discrimination, better classification without using any machine learning based technique. Next slide, please. So after that, this next part, we have actually studied this classification of seizure and non-seizure EEG signals. And here subset Z, O, N, and F, they are combined to form the non-seizure class, and subset S from the seizure class. And here, similar to previous EMD method is used to decompose the EEG signal into set of AMFM components or IMFs. Then we have computed bandwidth due to AM and FM parts, and then we have designed the feature space. Next slide, please. And here you can see the first four IMFs in the first figure. Bandwidth due to AM shows the difference between seizure and non-seizure classes. On the other hand, if you see the remaining IMFs, 5th to 8th IMF, then actually there is no difference between the bandwidth due to AM parts. And same thing we have observed in the bandwidth due to FM. In the next slide, please. So here you can see this bandwidth due to FM. The first four IMFs, they are giving actually better discrimination. And when you see the 5th IMF to 8th IMF, then there is no discrimination. So that actually, so due to that reason, we selected first four IMFs for the further processing. And also you can see there is no proper discrimination like earlier case. So there is no 100% separation. So that also motivates us to project these features into some higher dimension space where this classification can be done. So that is actually for like this is the whole purpose of like using machine learning based approach. So we are going in a higher dimensional space where this classification can be done. So next slide, please. And this whatever you have seen using these graphical plots, graphs, here it is also can be used based on the probability values of the feature. So like first for IMFs, the probability value that is actually less than 0.05 and they are statistically significant. And the remaining remaining four IMFs, 5th, 6th, 7th, 8th, there you can see they are not statistically significant. So due to that reason, this first four IMFs bandwidth features have been used for further classification or using machine learning techniques. So here we have used least square support vector machine classifier in order to have better classification. Next slide, please. So it is very support vector machine is actually very like a simple concept for the classification. We use margin and we some threshold and we go the high dimensional, two dimensional, just in this case, and we find out the different regions for the different pin classes. And this least square support vector machine is the improved version of the support vector machine. Here, instead of constraint, like we have say a set of linear equations, so it is low computation. It has low computational complexity. So equation 6, you can see this is a general model of the support vector machine for two class or binary class classification problem. Fx equal to sine wtgx plus v. So w is the L dimensional weight vector, gx is the metric function, v is the bias, and sine is the plus or minus. So if plus sign is coming, then it is one class and minus is another class. Next. It's a very simple block diagram of the least square support vector machine based classifier. You just take set of the features and then you select some features for the training purpose. Then you train the classifier together with the kernel functions parameters, and then once you have trained the classifier, then we use remaining set of parameters training as a features for the classification purpose, for the testing purpose. So that is that actually, if output is 1, then is one class, output is -1, then is another class. So in that way, this binary class classification problem can be actually solved out. You can identify the classes using such kind of classification system, whether it is CGR or non-CGR. Next slide. And in this work, the following kernel functions are used. Polynomial kernel, which is defined by the equation 7, where L is the degree of the polynomial, and radial basis function, which is defined by equation 8, where sigma controls the width of the RVF kernel. Next slide, please. And this Mexican head wavelet kernel function can be defined by the equation 9. And here actually you can see mathematical representation. And the Morlett wavelet kernel function is defined by the 10, equation 10. And so these all actually these kernel functions we have used for the classification performance measure classification task. And in order to measure the classification performance, we have also used classification performance measures, which are sensitivity, specificity, and accuracy. In this slide, you can see the mathematical expressions. And sensitivity, the proportion of epilepsy are correctly detected by the algorithm, and specificity, the proportion of the segments without seizures or non-seizures correctly detected by the algorithm, and accuracy, the proportion of the correctly detected seizures and non-seizures by the algorithm. And in these expressions, TP is actually TP represent true positive, FN represent false negative, and TN represent true negative, and TFP represent the false positive. So in that way, this all actually these equations can be interpreted. Next slide, please. And this here in this slide, you can see the sensitivity, specificity, and accuracy of the IMFs. First for IMFs for different kernels, polynomial, RBF, Mexican head, and Morlett, and kernel parameters are obtained based on a trial and error method. And then this perform measure sensitivity, specificity, accuracy, and you can see this tenfold cross validation case. The Morlett kernel function gives you the better performance for classification of seizure and non-seizure signals using the second IMF. That is those entries are shown by the bold letters, and that also we actually validated. Next slide. Validated using this region of receiver operating characteristic ROC. So that is actually area under ROC that measures actually the strength, the performance of the classifier. So if it is coming to 1, this is like ideal, and it's less than 1, it shows like performance indicating. So in all classifiers like polynomial, RBF, Mexican head, Morlett, we have studied this area under ROC curve, and we have seen in case of Morlett, it is coming out to be equals to 1. So it is a very good performance. So this area under ROC curve, that also validates actually the good performance of the Morlett based classification, Morlett kernel based classification. Next slide, please. And this is very important result for the testing. Actually, this is for testing phase of this feature space. And here you can see there are two separate regions. And like if you record the EG signal and you decompose into using EMD method, determine the IMFs, then compute the select the second IMF, compute the bandwidth features and map in this feature space. If it is coming out the dark region, then we call it seizure, otherwise it is non-seizure. So it is like automatically one can detect, even using such kind of framework, this mobile or smartphones can be used to install these algorithms, to implement these algorithms, and nicely you can detect epilepsy in the initial stage and timely treatment can be carried out. And that is actually, so this is smartphone. If you are having a smartphone with you, it doesn't mean that you are smart. But if your smartphone is doing smart work, you are detecting epilepsy, you are detecting brain diseases in the initial level, then you are really smart. So a smartphone actually can do a lot of smart activities using such kind of softwares. Next slide, please. So there are a lot of actually work has been done in the literature for this classification problem, and you can see there are various signal processing machine learning techniques, and in the right last column of this table there are various performance have been obtained actually classification accuracy for this study database. And our proposed method is based on the empirical mode decomposition bandwidth features least square support vector machine classifier, and it gives you actually accuracy between 99.5 to 100. So that is actually the better than the other methods in the literature. And next slide, please. After that, we have actually proposed the epileptic seizure detection algorithm. This is actually for real-time detection, and such kind of detection algorithms are very useful when you want to detect epilepsy in real life. So, like for example, somebody driving a car and a person can get the epilepsy attack, and such methods can detect epilepsy in advance, and then car can be stopped, and these drugs, epilepsy drugs, can be provided to that person, and in that way he or she can bypass the attack. So that already we have seen earlier, like if you do the visual inspection of for every time of this signal is very time consuming, it may not be possible also for long data recordings. So when seizure occurs, these automated detection methods are very useful for providing required treatment for the epileptic patients. So here actually we have used instantaneous area parameter, which we have defined earlier for the epileptic detection, and the EEG data set, which is publicly available at the University of Freiburg, Germany, has been used in this work. Next slide, please. So this data set actually includes invasive EEG recording. Invasive means they are recorded from the inside of the brain, and from the 21 patients suffering from focal epilepsy. So there are two types of epilepsy. One is generalized epilepsy. It can take place anywhere in the brain. And focal epilepsy, it makes the region specified, and a specific region. From that always it originates. So now in case of focal epilepsy, around 80% cases actually, this is drug resistance epilepsy. Like epilepsy, if the medicines doesn't show any effect, so only option which is left, that is surgery. So in order to have surgery, you have to identify that region of the brain where the surgery can be carried out, and that actually signal processing machine learning techniques play important role, and you can accurately identify that reasons. And so this in this our group has done some work to identify focal and non-focal regions based on the signals, and that actually are not included in this talk, but you can see our other papers for the same. So here actually this focal epilepsy, the subjects actually there were 21 patients that suffering from this disease, epilepsy form, and this data set has such recordings, such EEG signals, and this EEG data has been acquired using digital video EEG system with 128 channels, and sampling rate is 256 hertz, and 16 bits 8 analog digital converter has been used. And in this study, 3 inter-source records of 9 patients with focal epilepsy originated in the temporal lobe region has been selected. So total we have 90 segments per each channel, and 51 of them without seizure, and 39 segments denoted as having only one seizure. So now actually we have to just detect that particular seizure. So we will see the results. Next slide, please. So it's very nice actually to see the signal actually has like a seizure, but you cannot see it. It is not easy visible. But when you perform the decomposition like IMF 1, 2, 3, you see this seizure becomes boosted. It shows clearly like in the presence of the IMFs. So this actually these IMFs now, if you compute the extended area parameter, next slide please, then it will be more evident, more visible, so that you can see. Next slide please. So now extended area is actually, it nicely shows the presence of the seizures, and then actually we have compared our the detected points beginning and ending of this seizure attack using our proposed approach, and also the method benchmark or the ground truths which are provided by the neurologist. So you can see this dashed lines in the beginning and ending of the seizure, they are provided by the neurologist, and the points which you see in the form of circles, that is proposed by the actually our bias, and that actually, so this result shows that whatever actually the points we have detected in the seizure beginning and ending, that is actually perfectly matching with the neurologist, that whatever neurologist has opinion. So in that way, our proposed framework can be used as an alternate of the neurologist. So like in the absence of neurologist, even you can detect such beginning and ending of the seizure. Next slide, please. So in order to have actually more reliable epileptic seizure detection based on the status area of IMFs, this has been performed by the following decision rules. So first decision rule requires the computation of the threshold of status area of IMFs to be signal for all channels, and the threshold of the nth IMF is computed by the equation 11. And second decision rule requires the identification of those seizure activities which are actually present in at least 2 of the 3 instantaneous area of the IMFs of each channel. And after that, third rule requires making an inter-channel decision based on the identification of those seizure activities which are actually available in at least 2 of the 3 channels, which presents actually where presence of seizure activity in each channel is decided by the rule 2. So by using these 3 rules, we actually we ensure that actually like if out of 3 channels, 2 channels are in the favor of a seizure, then we say this is the seizure activity. If out of 3 channels, 2 channels are in the favor of seizure free, then we call it seizure free. So based on the majority of the electrodes or channels, we take the decision. Next slide, please. So this is the actually this table, you can see the performance evaluation parameters for the proposed framework. So patients, number of segments, true TP, true positive, true negative, fast positive, fast negative, then sensitivity, specificity, PPV, positive predictive value, NPV, negative predictive value, and ERD, error rate detection. So these, you can see sensitivity, specificity, PPV, NPV, they are expected to be very high, and they are high also in the proposed method. On the other hand, ERD is expected to be less because it's error, so ERD is coming out 24.25%. So the whatever methods, whatever results we are getting, our proposed framework, they are actually they are like what we are expecting. So they are in the favor of the expectation. So it is desirable results. Next slide, please. And we have compared our epileptic seizure detection framework with the other existing methods in the literature. Those have been studied in the same database. So Oras 2009 use energy of IMF V signals. Korea 2009 they use energy of EG signals. And you can see sensitivity, specific PPB and PPRD. In all cases, our method actually giving better performance compared to the other existing methods in the literature. Next slide, please. After that, this sleep stages also actually, when you sleep, then there are various stages for sleep. So like, and they actually highly correlated. Even like you are changing different stages of the sleeping in the night, and you don't know. So they are actually highly correlated, and it is very useful if you identify these sleep stages based on the EEG signal. Is very complicated work, and there, of course, there are multi-class classification problem. So it is a very nice use of the signal processing machine learning techniques to identify the sleep stages. So the oldest sleep stage technique that was proposed by the RNK method and RNK standard, that was 1965. According to that, the sleep stages, they actually have 6 sleep stages. So like awake, non-rapid eye movement, S1, S2, S3, S4, and rapid eye movement. So 6 rapid eye movement, that is actually, that is the, in India we call it Brahma Muhurta, like morning time, 3 o'clock to 5 o'clock. And this rapid eye movement, that is actually very useful sleep stage. And this is responsible for the dreams. So like if in rural areas, actually people do a lot of interpretations of the dreams. If you have seen dream in the night around 12 o'clock, they don't take it seriously. If you have seen in the dream in the morning time, in rapid eye movement stage, then they take it seriously, they interpret it. So there are various interpretations for that particular stage, rapid eye movement. And other finding in the literature, like alcoholic people, if they take alcohol, they don't recover, they don't have this rapid eye movement stage, because that is not coming for that. They don't sleep in the deep. And this alcoholic people, you find that they are in the, actually in some way they are accumulating the sleep disorder, because that last stage, that is deep sleeping due to rapid eye movement, that is actually is not coming for them. So they are not even sleeping properly. And recently, another sleep stage standard has been defined. So initially of now 6 sleep stages that American Academy of Sleep Medicine. Next slide, please. In 2008, 7-8, this is like American Academy of Sleep Medicine, which has come up with a new sleep staging system. So in that, actually we combine sleep stage S3 and S4 of RNK standard into single stage, that known as slow wave sleep or deep sleep. So now instead of 6 sleep stages, we have 5 sleep stages. And manual method for plasma sleep stages is a very time consuming task, because there are 6 stages in the RNK standard, 5 stages in the American Academy of Sleep Medicine. So due to that actually reason, there is a lot of, and they are highly correlated, and there is prone to inter and intra-scorer variability. So due to that reason, there is a lot of actually motivation for classification of the sleep stages using actually the EEG signals and using signal processing machine learning techniques. Next slide, please. So this is a proposed method, and we have EEG signals of sleep stages S0, S1, S2, S3, S4, S5, so 6 stages, and they may be for American Academy of Sleep Medicine, they can be 5. Then we apply time frequency representation that is computed using pseudo Wigner distribution method. And once you have this time frequency representation analysis, then this represent the energy as a function of time and frequency. Energy is a positive quantity, so we can convert this energy into in the form of intensity of an image. So this time frequency distribution is converted into time frequency image. Then we segment time frequency image of each signal based on the frequency bands of the rhythms, and then actually these features based on the histogram of sub images of each signals has been carried out. Then we have given these features as input to multi-class least square support vector machine classifier, and that actually classifies these sleep stages, like if it is American ASM, American Academy of Sleep Medicine, has 5 sleep stages. RNK standard, then there are 6 sleep stages. So nicely you can classify them using this signal processing machine learning technique based framework. Next slide, please. So here actually we have used this data set, which is publicly available online by Physionet website, and this recording has been obtained from the 8 males and females whose age vary from 21 to 35 years without any medication, and the recording includes horizontal FPZ, CZ, PZ EEG signals, each sample at 100 Hz. So according to RNK standard, the EEG data has been divided into 30 segments epoch. In total, there are 4,700 epochs. that is from actually different numbers from awake S1, S2, S3, S4, sleep stages. And these actually these signals have been recorded in the night during 12 o'clock to 5 o'clock. So like 5 hours time is sufficient actually to opt and or to get these actually these sleep stages. Epoch means this is actually this is a segment. So 30-second that actually the size segment. This is like window of this interval of this EEG signal. You cannot take entire EEG signal, so you have divided the signal into different epochs. So epoch is like segment of that obtained from the large EEG signal into narrower EEG signal. So this is narrower EEG signal, but its size is determined by the epoch. So we call it epoch because it has relatively less duration compared to the entire EEG signal. Is it clear? So this is a segment which we are considering for the processing. So now next slide please. So this is smooth pseudo Wigner-Village distribution which is defined by the equation 11 actually has been computed, and one of the example of this computed smooth pseudo Wigner-Village distribution can be seen in this figure. And here this intensity image actually this energy that you see in time frequency domain converted into intensity image. So next slide please. This is the obtained grayscale representation of time frequency image or gray time frequency image based on the smooth pseudo Wigner distribution of rapid eye movement sleep stage of EEG signal. Next slide please. And then this is the gray and binary sub images of this time frequency image obtained by the segmentation of the time frequency image using frequency bands. So this frequency scale is segmented. So the delta rhythm, theta rhythm, alpha, beta and gamma rhythms. So different frequency ranges are used to segment the time frequency band. So in that way we have now segmented time frequency images or sub images corresponding to different rhythms. Next slide please. Then we have computed histogram of the gray and binary sub images of time frequency image corresponding to frequency bands of the delta rhythm, theta, alpha, beta and gamma rhythm that you can see these are histograms. Next slide please. And then actually we have proposed these features based on the histogram of sub images for the EEG signal analysis. That maximum count of pixel intensity in the histogram of gray sub images which is defined by the equation 12, and spread in the histogram of gray sub images is defined by the equation 13. Next slide please. And aspect ratio in the histogram of binary sub images defined by the equation 14. And next slide please. So now this entire problem that you see in the sleep issues classification, that is multi-class classification problem. So earlier we have seen in case of epilepsy, this was actually like two-class classification problem. But here now you have multiple classes, like in RNK standard you have 6 sleep stages, in American Academy of Sleep Medicine you have 5 sleep stages. Now we want to classify these multi-classes. So this multi-class least square support vector machine that has been used to actually classify these multiple classes, and that decision function of multi-class least square support vector machine it is provided in equation 15. Here you can see, and there actually is even kernel is also multi-class classifier. So like different values of k can give you the small k gives you the different kernels for the classification purpose. So next slide please. So we have actually in this work we have used following kernel functions: radial basis function RBF, which is shown by the equation 16. Next slide. And Mexican head wavelet kernel function, Morlet wavelet kernel function, which are defined by the equation 17, 18 respectively. Next slide please. So here actually now you can see what is the need of actually a segmentation of time frequency image. So that actually we have studied. Now is audible?
Yeah, audible, sir.
Yeah, some problem, but their mic was disabled. I don't know, but now it is fine.
Yeah. I'll check, sir. Yeah.
Okay, now it is fine. It is working. It was actually disabled. Now enabled. Okay. So here you can see when you perform segmentation of time frequency image, then actually there is huge improvement. And without segmentation of time frequency image, there is classical performance is not so good. So you can see when you use same RBA, Mexican head, modeled kernel functions, and awake, S1, S2, slow wave sleep, S3 and S4, rapid eye movement, RAM, and total accuracy you see. Without segmentation and with segmentation, there is a huge difference. So for example, suppose case of Morley, without segmentation of time frequency image, if you see that is 79.99% accuracy is coming total. On the other hand, if you perform segmentation using this Morley, the same kernel is giving you 92.93% accuracy. So that is actually huge improvement. So this motivates us to use segmentation of time frequency image. Then there is more information is actually available, more features are available to classify, and the classifier is able to classify these classes in more better, more accurate manner. Next slide, please. So this is the confusion matrix for classification accuracy of the sleep stage of EEG signals for modeled wavelet kernel with window size of 64 samples. Next slide, please. And here actually, so this is RNQ standard. There is a lot of work has been done. It's the old standard, and these are the recent papers which shows the better performance than the other ones. So we have compared with the better ones. So Doros on curve, that's 2007 they use FFT based features error Markov model, and Burale and 2010 they use hybrid features and cluster based classifier using PCA. And these both methods gives you total accuracy 61.08%, 69.98%. And our proposed method, which is based on the time frequency image based features and multi-class square support vector machine classifier, it gives you 88.47% classification accuracy. Next slide, please. And American Academy of Sleep Medicine is very less work has been done, which is good direction. You can start doing some work in the direction also. So Sue and others 2013 they use energy-based features and Lemon neural classifier and got 87.20% accuracy. And our proposed method, which is time frequency image-based features and multi-class square support vector machine classifier, that gives you 92.93% classification accuracy. Next slide, please. So after that, there is another very interesting actually classification problem, that is human emotion classification. That is actually very useful, and there are various ways to classify the emotions like speech signals. Also, people use face images. So both actually can be manipulated. So the EEG signals they contain valuable information related to the different emotional states, which help us to understand the physiology and psychology of the human brain. And emotions which are measured by the EEG signals are more advantageous because it's difficult to influence electrical brain activity intentionally. On the other hand, this face image can be manipulated, and speech also can be modified. So this emotion classification using EEG signals are very useful to develop improve brain computer interface system, and a BCI system can be used for assisting the physically disabled and impaired people to interact with the real world. So for example, somebody not able to speak, and then EEG signals can be recorded, and different emotions can be used to understand the actually need of the person. Suppose he is not feeling well, then he will have different emotions. If after treatment he will have different emotions. So the effect of the treatment or state of the actually effect of the treatment also can be studied for the different actually subjects using these EEG signals. So that's very useful emotion detection based, and is one of the important actually part in BCI, where you can interact with the people, and the people have disability. So like Stephen Hawkins, he used to use a lot of BCI frameworks for interacting with the real world. He was not able to speak, but we can understand by these EEG signal processing based approaches, neural activities, what is actually information he wants to convey. Next slide, please. So this is the proposed method. We have experimental setup, then pre-processing, then multi-wavelet transform applied here as a signal decomposition technique. Then we obtain the subbands, then Euclid distance based features from 3D phase space reconstruction they have computed. Then these features are given as a input to multi-class least-square support vector machine classifier. Then you have nice classification of happy, neutral, sadness, and fear emotions. Next slide, please. So this is this actually EEG signals, the recording process. The EEG signals have been collected from 8 healthy subjects, 4 males and 4 females, whose age vary from 20 to 35 years during audio video stimulus. And the subjects were undergraduate students or employees from IIT Indore. And 16-channel EEG module BioPAC system in compliance to the International 10-20 system was used for recording EEG signals, and sampling rate was 1000 Hz and with bipolar montage for this study. Next slide, please. And this study has examined 4 emotional states, which include happy, neutral, sadness, and fear. And for this experiment, 3 audio video stimulus with 5 trials of each emotion from 8 subjects with F3, F4 channel of EEG signals have been used. And 480 EEG signals were used with 2-second duration. So here you can see this is a EEG electrode cap, and F3, FP1, FP2, this F4, these are the electrodes are used for the recording EEG signal. And this shows the arousal valence, this plot or representation of the emotions, fear, sad, happy, neutral, and whatever 4 emotions we have considered, they are covering into different regions of this arousal and valence block diagram or plane. Next slide, please. So here actually this is the complete methodology part. So here this you can see subject is watching video, and then EEG signals are recorded, and then we have EEG data. Then we perform pre-processing to remove some artifacts or some unwanted components. Then we apply non-state signal decomposition technique. Then we extract the features, and then these features we apply as input to machine learning classifier. Then it gives you a classification of the human emotions. So this in this work actually multi-wavelet transform has been used, which is the extension of the idea of a scalar wavelet, where multiple scaling functions and associated multiple wavelets are used instead of a single one. And this multi-wavelet actually offers many advantages, which include simultaneously expect orthogonality, short support, symmetry, and second-order approximation. So in this work, we have used 3 commonly multi-wavelets, so like GHM, CL, and SA4. Next slide, please. So once you have this decomposition, you have decomposed subbands. Then we apply 3D phase space reconstruction. So this is a very important tool for characterization of higher dimensional dynamic systems. And in order to extract the nonlinear dynamics of the sub signal which we obtain from the multi-wavelet transform, we have used the phase space reconstruction approach, and phase space reconstruction of subband signals can be expressed mathematically by the following formula that you can see this slide. Next slide, please. So this is one example of the 3rd level decomposition. So when you go 3rd level decomposition, there will be one approximation, 3 details. So there are like 4 subbands, and using CL multi-wavelet, and here the 3D phase space representation, 3D PSR, there is a lot of variability. Now how to quantify this variability, which is actually present in the various subbands, so that we have proposed the various features. So they will actually identify, they will measure the variability present in the subbands. Next slide, please. So first one is the mean of equivalent distance. So that you can see is measured by equation 19, expressed by equation 19. Standard deviation of equivalent distance, which is expressed by equation 20. So these 2 features actually they are based on the equivalent distance. They have been used to measure the variability present in the Euclidean PSR, phase space reconstruction. And next slide, please. So now we will see experiment results. We have used GHMCL assay for multi-wavelets, and we have obtained third level decomposition, and we got the 4 subband signals. Then we apply phase space reconstruction of subband signals, and then utilization based features are computed. And then actually these features have been used as input to multi-class square support vector machine classifier with RVF kernel, Mexican and Morley wavelet kernel functions. Next slide, please. And here also, since it's a multi-class classification problem, so we have used multi-class square support vector machine classifier because there are 4 emotions, 4 classes classification problem. And CHM SA4CL multi-wavelets, in this table you can see the kernel functions and parameters, they are computed based on trial and error methods. And then happy, neutral, sad and fear emotions, that you can see total accuracy. And in case of CL multi-wavelet, this Morlet kernel function actually gives you 91.04% classification accuracy. So that is better than the other multi-wavelet that we have studied. Next slide, please. Then actually this is the confusion matrix, the earlier slide. The confusion matrix of the Morlet wavelet kernel function, which are provided better performance. Multi-class square support vector machine classifier for the classification of human emotion from EEG signal with CL multi-wavelets. Next slide, please. And here you can see we have compared our actually proposed method with other existing methods in the literature. They use music, video, different number of channels, different signal processing technique, different classifiers. And the obtained accuracy were 82.29%, 66.5%, and all these studies are 4 classes. And our proposed method is actually gives better performance than the other existing methods in the literature, and gives the better classification performance. This is based on a multi-wavelet transform. Next slide, please. So now this whatever we have seen, that is actually univariate EEG signal processing. Now we will go for multivariate EEG signal processing technique that recently actually our group has started working in this direction. And till this point, do you have any questions?
Participants, you can ask the queries.
Or otherwise, if you want, then we can have later also. Means after completing this part, because it will take around 15 minutes.
Yeah, after 45 we can.
Okay. So, Dr. Rahulji, can we complete this part also? Then we can have questions.
Yeah, sir. Sure, sir.
Okay. Thank you very much. Thank you. So here actually now this multivariate analysis of EEG signals. Here we will consider all EEG signals to in analysis. Like earlier, what we are doing, we are considering only one channel at a time. But here we will consider all channels or all EEG signals recorded from the all channels. So first we will see empirical wavelet transform. Then this multivariate empirical wavelet transform actually we have proposed, and we have also proposed time frequency representation using this multivariate empirical wavelet transform, and that we'll see then is the application for seizure detection. Oh, next slide, please. So this empirical mode decomposition that actually you have seen earlier. It suffers from mode mixing problem, and it lacks mathematical theory. So like it is algorithmic nature, and it doesn't have any analytical formula. So recently this empirical wavelet transform has been proposed in the literature to overcome these limitations of the EMD method. So empirical wavelet transform that actually it has 3 steps. First step, we obtain the Fourier spectrum in the frequency range 0 to pi of the NRI signal by applying fast Fourier transform algorithm. Then we segment the Fourier spectrum into n contiguous segments using empirical Fourier transform boundary reduction method in order to determine the boundary frequencies. So once you know these boundary detection boundaries, then we design the empirical wavelets and which we use them as a band pass filter to each segment to separate out the components. So in that way we get the intrinsic mode functions IMFs. So our contributions in this direction include extension of EWT method for multivariate signals and time frequency representation of multivariate signals using EWT with application to epileptic seizure detection. So if you apply this actually EWT for multi-channel signals, and each channel will have different frequency spectrum. Each signal recorded from the channel will have different spectrum, different maximum minima, different segmentation, different boundaries. So number of components will be different. So it is actually problematic when you compare number of components. So like for one channel, if you apply EWT, then component may be 5, other channel there may be 6, other may be 7. So it is problematic how to compare. So this is actually this is a motivation for generalizing this empirical wavelet transform for multivariate case, and where these problems will not occur. So that is the motivation that we will see. Next slide, please. So we have proposed empirical wavelet transform based multivariate time frequency representation for analysis of multi-channel signals, and multivariate time series can be represented by this mathematical expression in the form of matrix, and where each element is actually single channel, so univariate. So arrangement of this univariate gives you the multivariate signal, and what we have suggested, instead of going for individual Fourier spectrum, let us go for the average Fourier spectrum of all channels, and based on that you design the actually filter bank to separate out, or design the wavelets to separate out the IMFs from the signals. And that same average spectrum, whatever average spectrum we are using, that actually can be applied to individual channels, so that number of IMFs will be same, there will not be different. So that is actually, in that way we decompose all channels, EG signals from all channels using this design filter banks, design wavelets using this average Fourier spectrum. And then for each mode, for the all channels, we determine standard amplitude and frequency. And next slide, please. So once you have instantaneous amplitude and frequency for each mode of all EG signals, then we determine joint instantaneous frequency and joint instantaneous amplitude. Mathematically, they are expressed by the following formulas, and there this is for distinct oscillatory levels. So like a particular phase. Then for this particular mode, from all channels we have got this joint instantaneous frequency, joint instantaneous amplitude. Then from that we can obtain multivariate time frequency coefficient at each oscillatory level by using this mathematical expression, and this can be generalized for all frequency oscillations or levels available in the EG signal. So this is for one particular frequency mode, this is for all modes. So in that way you have time frequency representation for multivariate multivariate channels or multi-channel signals like EG. Next slide, please. So actually we have proposed 3 features, three features have been proposed which based on the joint distance amplitude. There are mean of joint distance amplitude, which mathematical expression can be seen in the slide. Mean monotonic absolute amplitude modulation change also can be seen as expression, and variance of monotonic amplitude modulation change, which can be expressed also like mathematically, that also you can see. So these actually when you see the seizures epilepsy, that actually the detection of seizures is based on amplitude. So motivated by that, we have also proposed the features which are actually which are based on the amplitude of the signal. So this is the motivation. Next slide, please. So this is actually proposed epileptic seizure detection system, and here actually we have used PhysioNet CHB MIT scale data set, which is recorded from 23 patients, and it has 23 channels. And if you use all 23 channels for the processing or designing this epileptic detector system, then it suffers from huge computational complexity. So what we have done, we have selected 5 channels, and using this channel selection criteria, which includes first channel with least standard deviation. After detection of first channel, the other 4 channels based on relatively high mutual information with the first selected channel has been obtained. So you have 5 channels, then we apply this multivariate empirical Wavelet transform. That is designed, filter design is based on the mean spectrum. Then actually for this all 5 channels, we have 10 modes. Each channel will give you 10 modes, and then for each mode, now we actually we determine its amplitude and frequency for all 5 channels. After that, for particular frequency, particular mode, we have combined all channels together. So that is joint amplitude and frequency of each mode, and then actually we have extracted features from the different modes, mode 1, mode 2, mode 10, and then actually these features, they have some problem, and they are noisy in nature, that you will see in the coming slides. Then we have suggested feature processing, and once this feature processing given as input to classify, then nicely you can detect seizure and seizure-free EEG signals actually using such a multi-channel, multivariate scenario. Next slide, please. So this is very nice actually result. Here you see this 5-channel EEG signal, epileptic case. First case is epileptic seizure, and here you can see in time frequency represented that we have proposed, there is a presence of all frequency components, low frequency component as well as high frequency component. On the other end, if you see 5-channel seizure-free EEG signal, there is actually presence of low frequency component. There is absence of high frequency. So this actually can be used as a for the automated detection of the seizures. That actually is very useful for computer medical diagnosis. Yeah, next slide, please. So here you can see this features whatever mean of joint distance amplitude, mean of monotonic absolute AM, variance of monotonic AM change, all are actually noisy. So we have proposed this moving average filtering, and then actually filtered features are they look smooth, and the noise level is decreased. That is Hadamard product, and then we have suggested you just multiply these features together, all these 10 channels, 10 modes. Then you will have joint features, that is joint feature vector. Next slide, please. And that is actually very interesting result. So when you have joint features from these 3 features, and they're nice look like this. So that is actually epileptic seizure can be detected at that particular instant. That is not possible with the machine learning methods. So the signal analysis actually is very important part, which will give you the nice interpretation of the epilepsy. You can tell the what timing it is occurring, what is the localization, what is the spread, how long it is existing. So that actually that is explainable here. And this feature that you don't have this seizure detection in the case of raw EEG signals. Raw EEG signal, if you see, it is difficult to find out the epileptic seizure where it is present. But on the other hand, if you see the features, and nicely they are becoming higher at the location of the epileptic seizure. So this is the beauty of this method. Then we have given these actually features as input to machine learning based classifier. Next slide, please. So here actually there are many methods. This is one of the standard benchmark database where people have applied signal processing machine learning techniques, and they have got you can see the various classification performance in the last column of this table. And our proposed method actually based on tenfold cross validation gives you 99.5% class specificity, 97.9% is sensitivity, and 99.41% accuracy. So it is better than the other existing method in the literature. So next slide, please. So now this is the conclusion of this entire talk. This area which we have measured from the trace of the analytic IMS, which have circular form in the complex plane, can be used as a feature in order to discriminate normal and epileptic EEG signals. Bandwidth parameters, bandwidth AM, bandwidth FM by IMS can be used to formulate a feature vector which can classify seizure and non-seizure EEG signals in very nice with more accuracy. with very good classification accuracy. And we have seen Morlet wavelet kernel function together with LSSVM has provided better classification performance in the classification of seizure and non-seizure signals. And we have also seen that Paschen space system for detection of epileptic seizures from the EEG signals and instantaneous area actually which is obtained using moving window of the smallest size of the analytic IOs can provide good detection performance for rule-based detection of epileptic seizures from EEG signals. Next slide, please. And time frequency image representation makes possible to obtain histogram-based features of each sub-images of EEG signal corresponding to the frequency bands of EEG signal rhythms. And the histogram-based features are effective for automated sleep stage classification from EEG signals. And the classification results show that the Morlet wavelet kernel function of multi-class research support vector machine classifier has provided 92.93% accuracy sleep stage classification using EEG signals. And the mean and standard deviation of the Euclidean distance based on the 3D space reconstruction of sub-signals have been useful to measure the emotional changes of the brain. And the classification results have shown that Morlet wavelet kernel function of multi-class support vector machine classifier, the CL multi-wavelet, has provided 91.04% classification accuracy for the identification of emotions from single channel EEG signals. And mode alignment is the most important properties of a multivariate decomposition techniques. And a proposed method that is multivariate empirical wavelet transform align the similar oscillatory components across different channels. So the multivariate EWT based method has provided good detection performance for epilepsy diagnosis based on the scale EEG. Next slide, please. So thank you very much. So we have 15 minutes, and please, if you have any questions, please feel free to ask.
Participants, write your queries in chat box. Or otherwise you can unmute and ask. Sir, I have a question in that.
Yeah, please.
Yeah. So you are talking about the empirical mode decomposition and the wavelet transformation. I mean, EWT cases are there. And you have written so many papers and reports. A recent book I studied.
Yeah.
Yeah. But what about the modern non-stationary approaches like variational mode decomposition or TVF EMD like pattern? Is it viable for EEG or what you are excluding that thing for EEG?
Which one? Like I did not hear properly. This your
Yeah.
last part of the question. Yeah.
Yeah, I mean, talking about the variational mode decomposition or any time varying
Empirical mode decomposition.
Yeah, I mean, the variational mode decomposition and time varying filter based DMD approaches.
Yeah, DMD. Yeah. Okay.
So, if you tried those things and also, or otherwise, you're still sticking on the EWT methods.
Oh no. This is actually some of our previous work, and now actually we are trying to explore multi-channel signal processing like this multivariate VMD, multivariate EMD, multivariate EWT, this kind of, and there are various techniques actually, and all techniques have actually some advantages, some limitations. So sometimes even like many people still they are happy with Fourier transformers. So
Yes.
they modify Fourier transform in such a manner they can do their like whatever they want to have that processing. That so if you understand the research problem in the better way, what actually exactly you are looking for the solution, and accordingly that different frameworks can be modified.
Okay.
So, like for example, variational mode decomposition (VMD), and uh, eh, luckily it includes Wiener filtering structure. So the formulation optimization problem, when you solve the VMD, obtain the IMF, then there is a Wiener filtering kind of concept. So then they found that it's very good for noise robustness.
Yes.
So like if you are interested in noisy scenario, the signal decomposition, then EMD doesn't work. EMD is maximum minimum picking and everything will be there. But VMD will give you a nice set of modes. So it depends actually on our requirement. If we understand our requirements, then actually accordingly that technique can be modified. That particular.
Yeah.
So it
But
depends on the
but
like.
but every time we need the proper denoising one sorry for every application. So
Now this denoising, but now signal decomposition technique itself can be used for denoising.
yes.
So like the pre-processing, earlier we used to do pre-processing. Now if you apply this non-stacy signal processing techniques, that actually they can also remove some uncorrelated components, IMFs.
Yeah,
So
but my feeling is that the uh, while we are following this non-stationary algorithms in practical life, it is limited one. Whether it is in EEG or I mean in vibration or in power systems, wherever it is, actually people struggle to use this non-stationary algorithms. If it's still following, like what you said, the Fourier transform itself. Yeah.
non-stationary actually this is suitable everywhere.
Mm.
This actually, this world, whatever you see in this world, nothing is permanent except change. Change is always permanent, and whatever you see in this world, everything is changing. But people are not actually able to incorporate and see that scale change.
Yeah.
They are just ignoring that variation.
Yes.
If you want a more accurate analysis, like once the robots will come, human machine interaction, then people will understand that actually perception. You want to do more accurate analysis, then you will go for non-stage signal processing. Stationary Fourier transform, everything is lost. Fourier transform tells us what are the frequency present, but it can tell us what are the frequency at any point of time. So it is more general than the frequency. So whatever Fourier is doing, whatever this stationary signal processing, that is already inherent in non-stationary signal processing. But that actually linking people are not able to do. This is maybe some reason, but now for example this one of the right direction machine learning has come, that actually entire literature has turned that direction. So one direction is like you have convolution neural network, deep neural network, and that convolution neural network wants to have in the signal in the form of image, and real life signals are one dimensional signal, like for example ECG, EEG, speech, everything is actually one dimensional signal. Now time frequency distribution, if you go in time frequency domain, and you can have time frequency distribution, and time frequency distribution can be converted in the form of image,
Yes.
that is time frequency image, and you can use advanced machine learning algorithms in that domain.
Yes. Try to
So
face
there are
while using variational mode decomposition in the multivariate approach. It is limited to 24 channels. Uh,
That is why
there are
24 channels, still 24 channels, if you are using that good, actually now there's a lot of advantage in sensing technology. We have multiple sensors. Earlier, most of the most of the methods, they work only for single channel. At
yeah,
least now multi-channel, and if you use all actually joint analysis, that is very useful because everything is correlated in this body.
yeah,
One of the actually the one of the work actually I will share with the participants, where even you have multiple signals also, multi models like ECG from the different leads. You have your some heart sound signals, or this phonocardiogram, different actually models, different modalities of the representing the medical data. Then also we can use this multi-channel signal processing to get the correlated information. So like in ICU, you have multiple models, lot of, you will have many medical data. But how to get usual information out of all of that? So this multi-channel signal processing, multivariate analysis gives you an opportunity to find out the correlated information from that, all modalities.
Okay. Yes. Participants, do you have
This
any other
is
query?
seismic data, earthquake, civil engineering. A lot of work done is best for communication also. But
Actually, in my literature, I think my past PhD studies, actually, I think I believe in it's seismic data or even a structural part is actually basic for frequency domain decomposition. I mean, frequency domain FDD part and all. I think so. It's
yeah,
all
so this
start from there.
frequency domain itself is in the time frequency domain.
Yeah.
It is subset. This general form of the frequency, time frequency is a general form of that.
Nice, sir. Is there any other queries from the participants? Okay, we can wind up, sir. Thanks for the on behalf of Amartha School of AI, and personally, I want to interact with you sometimes, so, so I'm happy for that, and yeah, thanks a lot, sir. Thanks for coming and part of this workshop, and I will send you the mail soon. Yeah. Bye.
Okay, thank you very much, Dr. Rahulji, for this opportunity. And I also want to thank all participants for attending this talk. If you have any questions, any queries, please feel free to write me. It will be my pleasure to answer your queries. Thank you very much, everyone. Thank you.
Thank you, sir.